It's finally time to put together all the individual ingredients that we have for the explicit formula and actually obtain the explicit formula. So as a recap, what we found is that as a series, zeta prime over zeta at s, so the logarithmic derivative of the Riemann zeta function, was equal to minus, and then it was the Dirichlet series, n from 1 to infinity of uppercase lambda of n over n to the s, where here lambda, it denotes the von Mangold function, is defined to be log p if n is a prime power, a power of p, and 0 otherwise. So we have this Dirichlet series representation, and we also found in previous lectures that zeta prime over zeta of s is bounded by t to the epsilon, right? It was some power of logarithm, and t to the epsilon is going to be good enough for our purposes in this lecture. So how we're going to proceed at this point is we are going to use Perron's formula similarly to what we did for counting integers. So let's look at the integral along the line 1 plus epsilon minus it to 1 plus epsilon plus it of zeta prime over zeta evaluated at s times x to the s ds over s. And now by Perron's formula and this observation that this is the Dirichlet series, well, we can say that this is equal to minus the sum n less than x of the von Mangold function evaluated at n, and then we have plus O of x to the 1 plus epsilon over t. And so this was Perron's formula. Okay. And now what we're going to do is going to do some complex analysis to evaluate this as the integral of some complex function. So just as before, let's look at this integral. So here we have our complex plane, and here we have our real part 1. So we've got our 1 plus epsilon, and we're just going to extend this here as a rectangle that goes very far into negative real parts, right? So for counting integers, we limited ourselves to stopping halfway through the critical strip. Now we're going to go further than this. So we're going to say that we have this contour that consists of 4 segments. It's a rectangle, C1, C2, C3, and C4. So this point is going to be 1 plus epsilon plus it, and this point is going to be, let's say, minus m minus it. And now let's figure out what this integral is, and let's bound the integral of this function on these pieces. So the integral along C1 of zeta prime over zeta of s times x to the s ds over s, this is what we're interested in. So when I say it's what we're interested in, I mean it is the quantity that appears on the left-hand side of Perron's formula. So, we're just going to leave it as is, and okay. So we're really looking to bound the integral along C2, C3, and C4. as before, the integrals along C2 and C3, the top and bottom segments, are going to be quite similar. So the integral along C2 of zeta prime of s over zeta of s of x to the s times x to the s ds over s, well, let's use this bound that we got to say that this is at most, this piece here is at most t to the epsilon. And so this whole integral is at most the integral from minus m to 1 plus epsilon of t to the epsilon times x to the, so this is going to be an integral in sigma, so here I'll write just x to the sigma. So here I'm essentially taking absolute values and invoking the triangle inequality. And of course, the absolute value of x to the s is x to the sigma. And then here we have this amount that is d sigma, and then we can bound s by t here. And this gives the bound, this quantity has an elementary antiderivative, and it is, we can write it as x to the 1 plus epsilon t to the minus 1 plus epsilon, and then we also have this this m piece here. So this is plus x to the minus m plus epsilon, or perhaps minus epsilon, because we got to divide it by a log. So, and then we still have a t to the minus 1 plus epsilon. Okay. So that's these pieces. And then our integral, so there's some trickiness here, right? Remember that the bound that we got for this, well, there's a caveat. What we said is that for all s, there is an s prime such that s minus s prime is at most 1, so you're near s, and zeta prime over zeta at s prime is bounded in this way. Essentially what happens is that if we're really crossing over a zero of the Riemann zeta function, then we can't possibly have this bound, right? This logarithmic derivative will have a pole. So we're really saying is that there's some wiggle room. And what happens is we have these zeros of the Riemann zeta function, and we can pick our contour so that if we're too close to 1, we can actually sort of just scoot around it, right? So if we were set up to just hit 1, we could whoop, like that. And the details of exactly how this goes, I can refer you to Montgomery-Vaughan section 12, but that's the idea. So we still end up with the same bound here, but it is a little bit, there's some subtlety in what's happening. And then finally, for the integral along C4, this is the left edge of the rectangle, right here, of zeta prime over zeta at s of x to the s times x to the s ds over s. We can write this as an integral just in t, so this is going to be an imaginary part going from minus t to t of zeta prime over zeta of sigma plus, or sorry, here sigma is going to be minus m minus m plus it times x to the minus m plus it times dt over, and then here we have minus m plus it. Okay? And again, invoking our... so here, we need to choose m such that it is sufficiently far from even integers. So let's say it is uniformly bounded away from any integer. We can imagine, for example, that the distance from m to the nearest integer is at most 1 over 2023, whatever you like. And what that means is that as we integrate along this vertical line, we're not going to cross any of the trivial zeros of the Riemann zeta function. And that means that we can, again, just invoke our bound that this thing here is t to the epsilon. And what we end up getting is that this is at most the integral minus t to t of t to the epsilon x to the minus m, just taking absolute values here, and then we have a dt over, and okay, here we'll have a, it doesn't super matter, we'll just say over t plus 1. This is in fact good enough. And what we end up getting is that this is at most x to the minus m t to the epsilon. So this is pretty good, because if you compare to the situation for counting integers, here we had a power of t that was 1/2 or 3/4, depending on exactly how we were doing it, and this power of t had to be balanced against the power of t coming from Perron's formula, right? So in Perron's formula, we have an x to 1 plus epsilon over t, and so this means that we want to take t to be as large as possible, but then down here, so here there's no restriction, these parts are easy, but here we can't take t to be too big, because then this term will be enormous. But previously we had an x to the 1/2 t to 1/2 or something like this, and we really had to carefully balance these error terms. But here this is not the case, right? This t to the epsilon, this is tiny. We can basically take t to be as large as we like, and then just take m to be sufficiently small. So what we're going to find is that so our error term ends up being x to the 1 plus epsilon t to the minus 1 from Perron's formula. And then we have an x to the 1 plus epsilon t to the minus 1 plus epsilon coming from C2 and C3. Right, that was these parts. Of course, m is we're going to assume that it is positive, right? So this term is just not going to contribute compared to the top term. And then we also have this x to the minus m t to the epsilon coming from C4. And we want to balance these things. And what we can do is we can just say, say take t to be x to the to 10 to the 10. It can be something completely enormous. And then take m sufficiently large, right? Because take m to be such that this term ends up being small. So take m to be greater than going to have to be epsilon times 10 to the 10, is this right? And then we're sort of all set here, right? What we end up getting is that we'll just be able to take t to be enormous, and our error terms will actually completely vanish. So that's quite rare. It only happens when you have extremely good bounds on the on whatever you're integrating on vertical lines. So so here we have extremely good bounds on zeta prime over zeta, and that means that our error terms vanish. So that's great. And then, of course, there's one remaining piece, which is that in our contour, so C1, C2, C3, C4, we have residues that we need to add up, right? So the integral along C1 plus C2 plus C3 plus C4 of whatever is equal to 2 pi I times the sum of residues. So where are our residues? Well, we have poles whenever we have zeros of the Riemann zeta function. Because, of course, what we're integrating is the logarithmic derivative of the Riemann zeta function, and in particular that divides by the Riemann zeta function. So we have these poles coming from the non-trivial zeros of zeta, and we also have poles at the trivial zeros of zeta. So these are at s is -2, -4, ... all the negative even integers. Then we also have a pole right here coming from the pole at s equals 1 of, well, it's sort of wrong to say the pole of zeta, because it's really the pole of zeta prime, but it's the pole of zeta. And then finally we have a residue right here at 0 coming from the ds over s, right? When s is 0, we get a simple pole. So we have all of these. So we have these 4 categories of poles that we need to add up. So let's do them from right to left. So the pole at s equals 1, as we talked about previously, the residue at s equals 1 is 1. So the residue, of zeta prime over zeta of s is 1. And what that means is that the residue at s equals 1 of zeta prime over zeta of s times x to the s over s is x. This is going to be the main term in the explicit formula. Next, we have poles at s equals rho for non-trivial zeros of the Riemann zeta function. And again, as discussed previously, the residue at these non-trivial zeros of zeta prime over zeta was also 1 for all of them. And what that means is that the residue of at s equals rho of zeta prime over zeta of s times x to the s over s is x to the rho over rho. Okay? Next we have our pole at s equals 0. And here what we found was that zeta prime over zeta at 0 was minus 1/2 log of 2 pi. And that implies that the residue at s equals 0 of zeta prime over zeta of s, x to the s over s, is equal to, well, exactly that quantity, right? Because our, we have an x to the 0 as the thing that's multiplying. So just minus 1/2 log 2 pi. And finally, we have s equals minus 2n, n, 1, 2, dot, 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 so the trivial zeros of the Riemann zeta function. And for these, again, we found that the residue at s is minus 2n of the logarithmic derivative of the Riemann zeta function was equal to 1, and that implies that the residue of our integrand, the logarithmic derivative of zeta times x to the s over s, is equal to x to the minus 2n over minus 2n. Okay, so now let's put it all together. What we end up getting is that, so again, we have no error term, we have no remainder term, which is exceptional, but that's because we have such good bounds on the logarithmic derivative of the Riemann zeta function on vertical lines. So we end up just getting that the main term of Perron's formula, which was this. Oh, sorry. Right, so it was what we wrote right here, where capital lambda is the von Mongoldt function. And we found that this main term, or we're finding this main term, is equal to, so we have an x coming from the this term. That's right, there's we get no minus sign here because of the orientation of the integral. And then we get a sum over, sorry, this is going to be also there's a 1 over 2 pi I coming from just Cauchy's residue theorem has a 1 over 2 pi I. And so then we get a sum over the zeros, the non-trivial zeros of the Riemann zeta function. So let's say these are zeros that are not equal to, or that are not integers. And then we have an x to the rho over rho. Next, we have this minus 1/2 log 2 pi coming from our third term at s equals 0. And then finally, we have the sum n from 1 to infinity of x to the minus 2n over 2n. And now for this, what we can do is we can recognize this as a Taylor series. So recall that x to the n over n is minus log of 1 minus x, right? Just because this is the Taylor series expansion of this function. And so that means that this term here, sum n from 1 to infinity of x to the minus 2n over 2n, is equal to 1/2 log 1 minus x to the minus 2. And let me just check quickly that I didn't make any sign errors. So it looks like yeah, that looks right. And then it looks like I'm maybe supposed to have a plus here. Okay. So what this implies is that the sum n less than x of the von Mangold function is equal to, and this is an exact equality, which is quite remarkable, of the sum over the non-trivial zeros, so rho non-integer, of x to the rho over rho, and then plus 1/2 log 2 pi, and then plus 1/2 times log of 1 minus x to the minus 2. Let me check again just to make sure that I have all these signs right. So for a reference, the reference I'm using for this is Montgomery-Vaughan section 12. And now no, okay, I had the signs right the first time. Huh. Okay, well, what Montgomery-Vaughan is telling me is that there's no 1/2 here. I'm not sure why. Maybe I forget what that value is. It's telling me that there is a minus sign here, which is what I got the first time, so that makes sense to me. And then it's telling me that this has a minus sign, which I think also makes sense because I think I dropped a minus sign here, right? Yeah, there was a minus sign here, and so, okay. Yeah, so this is what you end up getting, and yeah, the reference I'll give is Montgomery-Vaughan. The theorem number is 12.5. And what is really exceptional about this is that this is an exact equality. We're saying that here we have a sum over not quite the number of primes less than x, but something very close to that. We're getting a log p weight for every prime less than x plus the prime powers. And this is saying that that sum is asymptotically x, and then the difference is actually given by the sum over the zeros of the Riemann zeta function, right? So this you should think about as x to the 1/2-ish, right? This is about square root x, because the Riemann hypothesis says that these zeros have real part 1/2. And then you have these correction terms, which of course are very small as x gets large. But it's quite cool that there's really no error term at all in this. This is an exact equality, and the right-hand side is completely explicit. And so this is called the explicit formula for that reason. And you can repeat the same kind of thing with pretty much any L function, where you will take the logarithmic derivative of that L function, write that logarithmic derivative as a Dirichlet series using the Euler product to write it as a sum over prime powers, and then also look at that as a function of a complex variable, figure out where the poles are, etc., etc. And if you can control the growth on vertical lines very well, then you can once again get an approximation, or you can get an exact identity called an explicit formula that has no remainder term. You just give it exactly. And even if you do have a remainder term, O of x, some power of x, it's still reasonable to call that an explicit formula as long as the left-hand side is a sum over prime powers for the Dirichlet coefficients, and the right-hand side is asymptotically some power of x.